So I sent Nancy a text early this morning, and she just now texted me back. That shows you how busy she is. So, motor controls, introduction to electricity. So most of this you got, we only require you to have intro to engineering here, which is just basic Ohm's law and simple single resistor series circuits. But we're going to have to add a little more to that for that, so y'all need to really pay attention to this. So this is some of the things that we're going to talk about in here. Let's see how many of y'all know. We need to know what is an electrical circuit. Now, what is an electrical conductor? What's an electrical circuit? Anybody know?
Source with a load and complete path of current.
Yeah, but we got to have conductors, right? So that would be the
Conductor.
But technically, it's a complete path for current flow, which it consists mainly of a source, a voltage source, then conductors and a load, right? And usually a control device. Anybody know what is an electrical conductor? That's a type of conductor, but what is a conductor?
Something where current flows.
Yeah, it's got almost zero. It's got very, very low opposition to the flow of current, right? They don't do work. They have a function in a circuit, but they don't do work. Work is, people don't understand work and function, right? You understand? What is an electrical insulator? This is something that's got extremely high opposition to current, right? What are the two most widely used conductors in electricity? Copper and aluminum, right? What's the best conductor of electricity?
Gold.
No, gold way down there.
Conductor.
Silver's best conductor. Yeah, we're gonna look at this in a minute. What is voltage, current, and resistance, and power? Now, power is something we're gonna pick up on. If you had DC, you understand power. If you had intro, you don't understand power yet, but we'll look at that too. Well, we need to know the difference between DC and AC. We're going to be dealing probably with AC and here, and AC and DC are not the same. So we're going to learn some terms, cycle, frequency, and hertz. We're going to learn the difference between an open and a short. This is one of the most misused terms in the electrical trade. What's required for a basic circuit? We'll look at what's the difference between series parallel and series parallel. We're going to pick up a new term that if you've had AC, you understand this. If you hadn't, we're going to have to learn up another opposition called reactance. And we're going to look at true power and apparent power, plus a lot of other neat stuff too. So if you know the answer to all these, then you're going to be okay. This is a chart that shows us the conductance of metals, and it goes from best to worst. So you know silver is the best conductor of electrical, best known. It don't mean there's not something out there. This is the best known metal that conducts. Why don't we use a lot of silver? Very expensive, right? You understand that. And also it's copper. Copper is one of the commonly used metals. This guy here is pretty good. I mean, up here we're talking about a difference between 6.2 Siemens per milli, and then this one is 5.69. So copper is extremely good conductor, right? You understand? Then we have what we call a yield copper. This is when they run it through heat to get it more malleable or make it softer. We use this a lot. It's not as good as pure copper, but it has better strength characteristics. So gold is actually the fourth one down the list. But the problem, a lot of people say gold because gold is expensive, right? You understand? A lot of people think that the more expensive it is, the better it is, but that's not exactly true. That would be like going to ITT Tech and coming here. Right, you understand that? So when you went to ITT Tech, you get an associate's degree for about $45,000. Was it any better than you got here? No. In fact, ours is probably a lot better. In fact, in our opinion, it is. So just because it costs a lot of money doesn't mean it's bad.
Now they're closed.
Yeah, and they're closed. Fine. When we first merged, that was one of Dr. Ward's saying that we're going to put ITT Tech out of business. It took about 10 years to do it, but they finally went out of business. Aluminum's way down the list, but we use aluminum a lot for high tension or high voltage lines, and we'll look at that one. And then the rest of them are just empty. So we use a lot of copper. We use a lot of copper alloys. We use a lot of copper that's plated. We use a lot of copper, and we use a lot of aluminum. Aluminum is used commonly for electrical distribution purposes. So silver is commonly used as a plating. So if you took a wall switch out, all your wall, and you look where the two, so wall switches, they make electrical circuits by just touching two wires together. So we want to make sure where those two wires touch is extremely low resistance, right? You understand? So they'll put an extremely thin coat of silver on there. So all our relay contacts, most of those have a silver plating on there. And they do that to reduce resistance, right? The primary conductor is still copper, but the copper is plated at the point of contact. And it's extremely thin, people. That means, and silver oxide is just as good a conductor as silver. So silver rust is a real good conductor. So silver will turn gray on you. And we have people go out there and they'll see these contacts and they'll be gray, and they get out their file and file it down. And then they get down to the wall. Get down to the copper, and it works real good, but copper has a real high, copper oxide is a bad conductor. And now you have something that'll work for a little while, but after a while it stops working. So never file these contacts. They have what they call burnishing tools, which is extremely fine grade. Copper is extremely good. Gold is very good. We use this on a lot of plating on things that's going to be exposed to the environment. And they're even getting away from this. For years, if you looked at what we call a motherboard inside a computer, everything that was exposed was gold plated. And now they use a lot of tin because tin has a very low oxidation rate too. What they finally realized was that by the time tin corrodes, the computer is obsolete anyway. So we don't use much gold plating there, but if they're going to send anything up in outer space or something like that, they use a lot of gold plating because it doesn't oxidize, right? You understand? So, they've dug gold coins up that's been in the ocean for years. And they crack them barnacles off there and it's what? It's just as good as it was when it went down there. So that's the biggest advantage of gold is it doesn't oxidize, has an extremely low oxidation rate. Copper oxidizes. Silver, aluminum, this is commonly used for high voltage. Now, aluminum has more resistance to it, but we'll talk about why we can get by that later. So copper and aluminum are the most used conductors out there. A lot of copper, a lot of it. Everybody understand what a force is? A force is an interaction that attempts to change the motion of an object. And work is the transfer of energy from one physical system to another, especially the transit. So y'all can read this as good as I can. This is usually measured in joules, ergs, or foot-pounds. Over here we use a lot. Foot-pounds, yeah. So if you're familiar with torque wrenches and that kind of stuff, that's what you're doing. You're putting a pressure which generates a force. By the way, you can't have a force unless you have a pressure. Everybody understand that? A lot of people get those confused. Power though, this is what power is. So when we say it doesn't do any work, we have a lot of things that have functions in the circuit, but they don't generate power. And power is the rate of doing what? Work. We can do force divided by distance or force times speed. Now in our formulas, this is electronics, right? You do what? Force times speed. So the longer the distance, the faster the speed. So that's why force times speed is the formula we're going to use for power. What's our force? What's the force pushing our electrons? Starts with V. Voltage. So that's what voltage is. And what are we pushing? Pushing electrons. And we call it current. And the rate is called amps. So amp is actually an indication of the speed. So basic stuff. All electrical devices operate from electrical current. Y'all understand that? So if we have voltage without current, we have no work. We have a force, but we don't have speed. Right? And we can't have speed without a voltage. So we got to have current. The amount of power produced by these devices is determined by the amount of current that flows through them and the rod, and the forces causing the current flow. Well, that tells you our power formula right now. What's the power formula for electricity? Anybody know? One of them? Yeah, current times voltage. So power is equal to V or E. We got two terms we use for power, for voltage, E, which stands for electromotive force. So if you read a book where they use E, that's just as replaceable, times current. And current is the rate. So 1 amp, anybody know what 1 amp is equal to? So Coulomb in motion, that's what it is. So a term Coulomb, we use the term Coulomb for a stored charge. Then as soon as that Coulomb goes in motion, it becomes current, right? You understand? Roughly 6.25 times 10 to the 18th electrons moving past a point in 1 second. And I counted it. Yeah. I don't know how they came up with that number, but it works out. So that's speed, right? You understand that? So force times speed. Our force is what? So when we specify 2 amps, we're specifying a speed. And then the force is going to be the voltage, right? And then that's why we calculate work. So if you got a watt meter, it's got to measure what? Force and speed. So that's what your watt meter does on the side of your house, by the way. The amount of current is controlled by the force and the amount of opposition to the flow. So if we're going to get work, we're going to have to push against something, right? I understand that. So we push against an opposition. Once we push against that opposition, then we're going to get power. But we have no opposition, we have no power. Everybody understand that? Yes or no? Of course, some of y'all already know a little bit about opposition. We call them resistors. But everything that does work has opposition. So all these lights up here, they're doing work, and they're doing more than just dropping the voltage, right? You understand that? Electrical current consists of atoms and electrons that have been forced to move by a difference of electrical potential. Okay. Everybody okay with that? The strength and the difference of electrical potential and the amount of opposition to the flow of the electrons determines at what speed the electrons move. So if I've got 0 opposition, then theoretically the electrons will move at infinite speed. Some materials, such as most metals, allow the electrons to move freely, while others, such as rubber, do not. For this reason, most metals make good conductors. Most things like rubber, air makes a good insulator. But these make what we call insulators. So what's the function of the insulator? So what's the function of a pipe? The walls of a pipe. To contain that push in there, right? You understand that? So what's the function of an insulator? To contain the push. All that power is looking for something to push that current through something. Everybody understand that? So insulators are to contain the push. So the thicker the insulator or the material of the insulator is determines how much push that thing can take in there. What's the function of the wire? To carry the current, right? So conductors are rated in amps. Insulators are rated in volts. Okay, y'all understand the difference? So we have a lot of good insulators. Got to keep that push in, especially when you start getting things close together. Like wires start getting close together. And we got that push. The 2 wires touch, and we have what we call a short, and that's not good, right? Unless we have insulators. But air is a good insulator. Alabama Power uses air as an insulator all the time. So what is voltage? It's the difference in electrical potential that forces electrons to move. What's current? That's the results of a what? Difference in electrical potential. What's resistance and reactance? So we're going to pick up another opposition that we got to understand when we move into AC. In electricity and electronics, we have two types of oppositions. We have something called resistance, which most of y'all should already have been in, because back in intro you learned how to do color code and all that other kind of stuff. You should have learned the color code. By the way, if you take any of my classes, you can ask people that's in there, and if you come up and say, Rich, I need a 220 ohm resistor, you know what I'm going to say? What's the color code? So resistance does not vary with something called frequency. Reactance varies with frequency. So reactance is dynamic. Thank goodness. If it wasn't for reactance, we wouldn't have cell phones, we wouldn't have radios, because it gives us a circuit that corresponds to frequency. So when you're in a car, we have what we call a carrier. And that's what you're doing when you tune your radio. Y'all ever notice the channels are like 93.7 megahertz? Well, what we can do with reactance is we can set up circuits that change with what? Frequency. So we can actually have what we call a tuner. So we can set up tune circuits. But we'll look at reactance before long. So a basic or minimum. So an electronic circuit is a complete path of current flow. Everybody okay? What is it using? What's the minimum requirements for it? You got to have a what? Voltage source. You got to have a source conductor. You got to have a what? Load. And you got to have a return source. Everybody understand that? Now, what's the common part? What's commonly in a circuit? No, we don't have grounds. I imagine ground is, we use ground a lot for outbound power. This phone don't have a ground. Normally, we'll show y'all this one. Normally we have some control device, right? You understand? So I've got my headlights on. When I go out there what can you do with your headlights? You can turn them off and you can turn them on. Well, that off and on switch is not part of a minimum circuit, so we got to add more devices here before long so we can control that flow. A good analogy is, of course, is human circuitry. If you understand the circuitry system, then you understand circuit. How does human circuitry work? We got what? What's these red ones? These are arteries. Right. And where do they go? They supply nourishment to the muscles, right? You understand? And then once that nourishment is moved, and brings back on veins, the wrong way blood back to the heart. What's pushing the blood? The heart. So the heart will be similar to our voltage source, right? You understand? My veins and my arteries are similar to the what? Conductors. My muscles are similar to the what? Loads. Exactly right. That's the loads. All right, you understand that? So there you go. And if you understand that, you're okay. If you lose any one of those components, what's going to happen? Probably going to die. You might could lose a load. So I've lost a load in this leg. All this down through here is paralyzed. I can move it this way, but I can't move it this way. It's strange. The heart pumps blood out through arteries, through veins, through muscles, and back to the brain. So what we're doing is we're providing that. So the blood is your power source of your body, right? You understand? It's what's powering your body. Your brain just sends impulses out to cause the muscles to move. So here we go. The voltage source is similar to the what? Heart. Current is similar to the what? Blood. Right, you understand that. So that would be current. Conductors are similar to the conductors, right? And muscles are similar to the what? Right. This is a basic circuit. I don't know where this came out. I don't know if it says in your book or not. So we have a voltage source. Here we're using a DC battery. Then we have conductors. We have what we call a source conductor and a return conductor. And then we have a load. Now normally what we have in here is we have something else. We have some type of device that lets us do what? Yeah, we call them control devices. So I might have a little switch over there. So these are our type circuits. Some of y'all are familiar with the first one. It's called a series circuit. Y'all play around with a single element series circuit. In intro and DC, you get into all of it. If you have DC, you get into all of it. But we can connect the load. By the way, a series parallel circuit is how you connect the loads, not how you connect the control devices. You understand the difference? So it's how the loads are connected. So what do we mean by series? All the loads are connected one after the other. One more load connected one after the other. The voltage provided by the source is distributed across the loads proportional to the loads up. I mean, biggest resistor would drop the most voltage. There's only one path the current through the loads is the same. Everybody okay? So this would be an example of a series circuit. So we have a voltage source. This is a generic source. We have two different symbols, one for AC and one for DC. And the loads are what? In series. So what happens if one of the loads open? Well, if one of the loads open, then we end up with an open circuit. If one of the loads short, we end up with a short. It's very important. You in the trade, you get out in the field. These people can call it anything they want to, as long as you understand the difference between an open and a short. Very important. Unfortunately, out in the world, most people, if they got problems electrically, they say they got a short or shortage. I like shortage.
So what you mean by open?
That's what we're going to talk about in a minute. So this shows us the path. We're getting there. So this is parallel. The voltage applied to each load is the same. So we're going to hook up parallel circuits. All loads are connected across the voltage source. The current is distributed to the circuit inversely proportional to the opposition. You understand that? Yes or no? So this would be a parallel circuit. So the load that has the least opposition would conduct the most current. So this is kind of opposite. So parallel circuits and series circuits are exactly opposite of each other. So what we do in a series circuit is the voltage is distributed through the circuit. So that means if I came over here and this is not the voltage. The voltage does not move. But every time you go through opposition, you lose pressure, right? You understand? So my heart does not move. But when they go up there, one of the first things they do when you go to a doctor is they check your what? Pressure. They don't check it at your heart. They check it where? Out here, right? Y'all understand that? It's very, very important. Well, every time you go through some type of blockage, you lose pressure. That's why we're all concerned about cholesterol and all that other kind of stuff. Are y'all concerned about that? So if I came over here, let's say we have 50 volts applied, and I come over here and this drops right here. If I put a meter right there, let's say it drops 10 volts. Well, what that means, if I come over here and use this as a common, and this is where I hook my meter to, if I measure here, I'd measure 50 volts. If I measure here, I'd measure 40 volts. Okay, everybody understand that? And let's say this come over here and this right here drops 10 volts. Well, what that would tell me is both those loads have the exact same opposition. Okay. So if I measured here, I'd measure what? I'd measure 50. If I measured here, I'd measure what? 40. If I measured here, I'd measure what? 30. So we're losing pressure. The voltage is not moving, but we lose pressure every time we go through an opposition, right? Y'all understand that?
Now, what we have to do, so if this guy here drops 10 volts, this guy here drops 10 volts, this guy here drops 20 volts, what does that leave me left? Let's change this to 5. Then this guy right here would have to drop what? 15. And that's what we mean. So all the voltage has to be distributed through the circuit, right? Y'all understand that? But it's going to be distributed, so which one would have the most resistance? Well, this would have the biggest R right here. So this would be the biggest one because it's dropping the watt. And which would have the smallest? This would have the smallest R. So the biggest resistor drops the most voltage. Now the current is the same, and that's why they drop the same voltage, because there's only one path for current to flow through the circuit. So the current is the same. So it's just like water entering one side of the pipe is going to be the same water coming out the other side of the pipe, right? Y'all understand that? Now when I get to a parallel circuit, if this right here is 50 volts, this is a straight piece of wire. So what would be across that one? 50 volts. What would be across this one? What would be across this one? 50 volts. What would be across that one? Which is pretty nice. So your house is wired in parallel. So you can take a voltmeter to any outlet and do what? You can plug it in there and it's going to measure the same voltage all over the place. Everybody understand that? Okay. Well, what's the difference? Well, if this guy right here is conducting 50 amps, this guy right here might be conducting 10 amps. This guy right here might be conducting 5 amps. This guy right here, what does that give us? Okay, let's say this guy right here is conducting 20 amps. Which one's conducting this one? Okay, so this guy would be 15 amps. So notice what's the same across all the circuits. Voltage, what's varied. Which one has the greatest opposition? Yeah, this guy right here. So this guy right here would have the big, right? And this right here would have the lowest opposition. So in a series circuit, the biggest resistor does the most work. In a parallel circuit, the smallest resistor does the most work. These suckers are just opposite. But what's nice about a parallel circuit is I can do what? Well, I can add and subtract loads. So if I come up here and take this load out, it's not going to do anything to this load. This load is still going to pull what? 20 amps, right? You understand that? It's still going to have 50 volts for it. So what can you do with your house? You can plug stuff in, you can unplug stuff, you can turn stuff on, you can turn stuff off. And just because you turn your kitchen light off, it doesn't affect your bathroom light, right? You understand? Because they're in parallel. So you can add loads and take them away. Series parallel, we're not going to have, we'll have series parallel, but we'll have to look at that. So this would be an example of a series parallel. So some of the loads are in series, and then we have what we call branches, and then the other ones are in what? Parallel. So we would treat this one like a series circuit. So if I had, if this was 50 volts, this guy right here might drop 25. This guy right here would have to do what? Drop 25. Over here, this guy right here might drop 30. This guy right here would have to drop 20. It has to drop the applied voltage. But across them, if I add these together, I would measure what? 50 volts. Now this is series parallel. Most of your electronic circuits are series parallel. We're going to do series parallel here, but we're going to do it kind of different, and we'll have to see it. By the way, our series circuits are going to be very neat. Series circuits we're going to do is only going to have one load in it, just like you did in intro. Our series circuits will be on one load. Our parallel circuits can be what? A lot of loads. Control devices. What do control devices do? These guys do no electrical work. So to do work, they have to drop a voltage, right? Understand that. They got to have opposition. Our control devices have almost no opposition at all. So right now, if I went back here and took my voltmeter and measured across this switch right here, what would it measure? Across the switch on this satellite right here. What would it measure across the switch? God, I hope not. It's going to measure zero. It has no opposition. A switch has no opposition. It does no work. So it has no opposition. It's got 0 ohms, right? So if you put your meter across a switch and you close it, your meter's gonna go to 0. V is equal to I times R. If you have no R, you can put all kind of current through it and you don't get any voltage. Now, the open switch, right here I would measure what? I measure the source voltage. So that's one thing you gotta learn right off the bat. That's got people hurt. They'll take their meter back there and measure across the switch. They measure 0 and they think the dang thing is not hot, right? Electrically hot. Then they stick their hand in there and get one. Shot. That's a common mistake people make. The connection to control devices does not attempt to determine if the circuit is series or parallel. So I can hook control devices in series, I can hook them in parallel, I can hook them, but that does not determine what the circuit is. The circuit is determined by how we connect the loads. Everybody understand that? But we'll use that term. We'll say, okay, these switches are connected in series, but that does not make it a series circuit. Some control devices using motor controls, we're going to have switches, we're going to have push buttons, and we're going to have devices called relays. We'll talk about that. Some of y'all have ran into relays before. So this is a basic circuit. This is what we run up with. So we have a what? We have a what? Voltage source. We have a what? Conductor. We have a what? A load. And then we usually have a what? A control device. Or multiple control devices. The name of this class is what?
Motor control.
So we're going to run motors and we're going to control them, right? Here's some control devices. So this is the top. These are just switches. Most of y'all familiar with most of these. They're in the wall switch there. We're going to use a lot of push buttons. Motor controls, we use more push buttons than we do switches, even though we do have some switches. These are the contacts of a relay, which we're going to look at. This is a float switch that we use in one of our classes. So it literally has a control device that opens and closes the switch when something gets up to a certain level. This is a foot switch. Some of y'all might have ran into some of these guys. So we got all type of control devices. And we're going to look at a lot of them because the name of the class is motor control. Right? Typical loads, we have these devices called relays. They're called contactors, motor starters, and control relays. We have lights, illuminations. We have solenoids that we'll look at. And these are just to mention a few things that could be loads in a control circuit. We usually don't put a motor in a control circuit. We'll show you how we do that. So the motor is going to be outside the actual control circuit itself. Symbols of the trade. You need to know the symbols of your trade. So what do we use symbols for? Well, represent would probably be a better term. So instead of we have different diagrams, and the book does a really good thing on that. How would we call a pictorial diagram? Anybody ever seen a pictorial diagram? Yeah, normally now when you buy a consumer product, like a new TV or something, how do they show you how to look that up? Well, they draw pictures of everything, right? We call that a pictorial. But them suckers take up a lot of room, right? You understand? So what we do is we pick up symbols that represent different things, and we put them in diagrams. If you don't understand the symbols of your trade, then you cannot read the prints that we use in your trade, right? We have a class called blueprint reading. Anybody had that yet? And you learn a symbol of a bunch of trades. And if you're going to be an electrician, you probably need to consider that class. Our wires are flexible, which means we can run them all different types of ways and still get the same results, right? HVAC systems or air conditioning ducts and plumbing, those things are not flexible usually, so they have to run those a certain way. So normally on prints, they'll show these guys how they're supposed to run it. Electrical prints, they just show us where they go, and it's up to the electrician to decide how to get that there the shortest route. So you need to understand the symbols of your trade. We have a thing called a schematic. We're going to be dealing with a lot of schematics in this class. So schematics is the term we use for an electronic circuit. Now some people misuse this term too, but technically this is what it is. And we use a ton of symbols. Y'all already know some symbols. What symbols do y'all know? Some of y'all probably know more than the others. Now, what's this a symbol for? Yeah, conductor. Now, what's this a symbol for? DC. Well, it is a symbol for a battery, but more technically, it's a symbol for a DC voltage source. So we have a lot of DC voltage sources that are not batteries, but they use the same symbol. What other symbol do y'all know? Yeah, I know this one, this resistor. So y'all should know these symbols. Most of y'all know the symbols for some switches. So that's a symbol for a single pole, single throw switch. I've learned that term too. This would be a symbol of a momentary contact push button. Not just any push button, momentary contact, which means what? Yeah, you press it, it'll make it. As soon as you release it, it goes. We got all these type of things. By the way, this is a symbol for an AC voltage source. So we come up here and we put that little squiggly line in it. Well, that's an AC voltage source. If I put an arrow through any component like that, what does it mean? It means it's variable or adjustable. Good. Everybody okay? So these are some of the symbols we'll look at in this class. DC voltage source, right? An AC voltage source, what's this? Resistor. And I'm a firm believer on that. Is that if you don't have a dot, you don't have a what? Connection. So some of y'all are going to lose some points in this class because you're just going to draw lines. So if we cross lines, so legally this is not a legal symbol. Of course, a lot of people use it. Where they have a crossing line and they come over here and do that. That's not a legal symbol. So what we know if we do this and don't put a dot, it means they are what? Not connected. If I put that, they are. So if you leave the dot off, it's going to be considered what? Not connected. And you'll lose points for it. This is a device called an inductor, which we're going to have to learn a little bit about that. It's just made up a bunch of coils of wire. This is a device called a capacitor. You need to have a basic understanding of these. You'll get inductors and capacitors and a lot of details in the AC. You take AC. This class we'll talk about it and what they're used, like motors and stuff like that. Now, this is a transformer with an air core. Most people draw it like this. What does the transformer do for us?
Stores.
Oh, store.
No. What is transfer? It steps up or steps down,
Voltage, yeah, but the current goes along with that, so we'll have to look at that. This is a symbol for what we call anybody know what we call this guy? We call this a single pole. Yeah, single pole double throw. Anybody know what that means? Yeah, well, the number of poles is basically the number of switches that's operated by the same operator, by the thing it does. So if I have two switches, that would be a double pole, right? The throws are the number of positions that switch can be put in. So this would be a single pole, double throw. But if I was to come over here and come up here and do this, and down below that, I'll put another switch. And then we put this little dashed line. What does that mean? They're mechanically connected. So they operate. This would be a what? No, this would be a double pole single throw. Two switches, but each switch can only be put in one position. That's a double pole. That's a single pole double throw switch. This is ground. And then this is a fuse. I didn't put a circuit breaker on here, even though I did. Anybody know the difference between a ground and a common? Some of you in my class already know that. Huh? I'm not asking for the symbol. I'm asking the difference between a ground and a common. So a common, the symbol for a common is this. The symbol for a ground is this. Three dashes, no more, no less. Okay. So what's the difference between a ground and a common? Not necessarily. God, I hope not. I mean, I'd be in trouble. My cell phone runs a common. My car has a common in it.
Common is just a common point of circuit.
Right.
Ground goes to earth.
Goes to earth ground, right. And you need to understand the difference. This is one of the most unusual, and even in technical manuals, this is a misused term. You need to know the difference between a common and a ground, right? Understand? So ground, we got this copper rod. They used to be copper rods, but now they're usually aluminum copper plated because they realized they didn't need all that copper in the center because it only made contact with the rod, the outside.
Wouldn't a chassis ground be actually a common?
Well, if it's connected to ground.
Just say in a car, it's not.
Well, that's not a chassis ground, even though people call it that. It is a chassis common. So to be a true ground, it's got to be connected to earth ground. Yeah. So your car does not have a ground. Your car has a common, but everybody calls it what? Yeah, everybody calls it ground. I mean, I don't hear chassis ground most often. They say your ground wire's loose or something like that. And you need to understand the difference. So your house has a neutral that is it is reference to ground. So they don't call that common, they call it a neutral. So yeah, if you call it ground, that's okay, but you need to know the difference between a common and a ground, because odds are if you get out in the field, any common connection, they're gonna call it a what? A ground. Now, these are some of our symbols. This is where it's gonna be important that you have your book. By the way, there's a new version of the book. We'll have to make sure that when I give you the page number, it's still the same. So what's the symbol? Now, these are in your book, so it's not nothing that you have to memorize now, but I'll give you the page number. We'll go back and look that up and see where it's at. But the one on the top left, what's this?
Circuit breaker.
A circuit breaker. Everybody understand what circuit breaker does? What circuit breaker does? When?
Increasing current.
Not an increase. Yeah, we call these are generically called O stands for what? Overcurrent protection device. So these are all fall in the categories of OCPDs. You ever heard that? OCPD. So circuit breakers and fuses would be considered that. I drew that under the relay.
Yeah.
The circle is a what?
It's a relay.
Cool. And we know, then of course, what's the next one? Indicator light. What's the next one? Momentary contact, push button, normally open. What's the next?
Push button on the.
Yeah, normally closed. Then we have what we call contacts. We have this symbol is for a what? Open contact. Normally closed. We've already talked about that. What's that? Single pole, single throw. Single pole, double throw. Double pole, single throw. Double pole, double throw. Once we get back to that, this is called a what? Select switch. Then some other ones we'll look at, it's called a plug switch, timer switch, pressure switch, plug switch. Of course, we got more. Let's see if we can find those. Anybody got your book? If you got our used book, if you get a used book, it should work out just fine. This is the newest version of the book. And I don't know what, they make little corrections. And one thing they like to do is move stuff around. Now, how much is the book? Anybody bought it yet?
How much is it? TRA.
It's TRA.
I don't know. If I can get it, maybe I can get one.
Huh?
But I can get one. No, James.
That's it.
Not you. No, James.
Our symbols in the new book start on page 731. And go through all the symbols. 136. Yeah, I think Wesley got his off of, or Thomas got his off of Amazon. My son was going out to Jeff State, and he ordered all his books from Amazon. And you know what plane they were on? A plane that crashed coming into Birmingham.
Come on, really?
True. They made it up for.
I bought a book for CIS class. They didn't offer a book, but they had it online, and it was easy to follow their class with the textbook.
Oh, for that,
Microsoft Office and all that stuff.
Oh, yeah.
okay, guys, let's take another break. 2 minutes.
Program that we're gonna be dealing with extensively this semester. We're gonna be dealing with two types of diagrams. We're gonna be dealing with what we call ladder diagrams or line diagrams, and also something called wiring diagrams. The two primary diagrams that we're gonna deal in. It should be obvious why these are called ladder diagrams, because they look like a what? Ladder. And guess what we call each one of these things right here? We call them rungs. Rungs, just like the rungs of a ladder. So what we have is, and this is a symbol for a what? No, it's not.
Which one?
That's not a symbol of a motor. It's a symbol for a relay coil. So this is a symbol for a relay. It's a special relay, by the way, called a motor starter, because of these things called overloads, and we'll learn about these as we go along. So what does a relay do? So what's a relay? Anybody know what a relay is? Don't necessarily have to be low voltage, but it can be, huh? Right, but it works off electromagnetics. Y'all know what electromagnet is. Y'all know the difference between a magnet and an electromagnet.
Electromagnet is when AC is applied.
Well, not necessarily AC. AC is a little harder to do than DC. DC is really safe. But this is a magnet. Okay. Now I cannot control the strength of this magnet. Whatever strength it's got is what it's got, right? You understand that? This right here is an electromagnet. Guys, I'm gonna